Hello and welcome back. Section 2.9, we get to work on equations with several variables. So these are basically formulas. So a formula contains one or more variables as part of an equation. So we'll start with a couple of formulas that most of you will see in your next course. So we'll start with mu is x minus z times sigma. So this is not a zero, this is a sigma. Those are Greek letters. Those are some things you'll see in your stats class. So this is an example of a formula. It contains one or more variables as part of an equation. So there's our equation. We have expressions on both sides. And as you can see in this one, we have 4 variables. So they could ask us to do a few different things from this. They could ask us to, for example, solve for x. So we look at how everything else that's on the same side of the x is related to it. And that is, in this case, they're related through subtraction. So we'll do the inverse operation. We'll do addition. So I'll add z sigma to both sides. And we have mu plus z sigma on the right hand side and x plus 0, or on the left side, x plus 0 on the right. And by the additive identity, x plus 0 is the same as x. And typically, once you've solved for it, usually it's thrown onto the left-hand side. So that x is the same as mu plus z times sigma. Now they could ask us to start with the same exact given formula and solve for something else. So they could ask us to take the same one, but instead they could ask us to solve for, let's do z this time. So we want z to have its own side of the equation. So that means we want to move the rest of this stuff. As you remember from your Mth093, 95 or equivalent that you took somewhere else and earlier work here in chapter 2, it's easier to use the addition property of equality first. So we're going to subtract x on both sides. So then mu minus x is worth 0 minus z sigma. And additive identity, we now have mu minus x is opposite of z times sigma. So the rest of what's on the same side of z is related through multiplication. So we'll undo the multiplication with division. So we'll divide both sides by opposite of sigma. So then z is worth mu minus x over the opposite of sigma. You may see that in one other form. If we factor out a -1 top and bottom, z could also be expressed as x minus mu over sigma. That's kind of the more commonly used one, instead of dividing by the opposite of something. But our goal is basically to use the properties that we've already worked on earlier in the chapter. This next example, we get to work with the distributive property as well. So this one we will solve for, what did I pick out? H. So A is 2LH plus 2WH. So this time I noticed that the variable I want by itself has multiple copies in the problem. They're both on the same side of the equal sign. That helps. So we can use the distributive property. So that is a very powerful tool that we have, the distributive property. Very helpful in a lot of situations. Now we just have a situation where we have something that we're treating as if it's just a constant. We're treating this as if this is just, say, a 5. If we were solving 12 is equal to 5x, we would divide both sides by 5. So here we'll divide both sides by the sum of 2L and 2W. So then H is A, cap A over 2L plus 2W. So let me have you all try one out. You're going to solve for x. We'll have pi times the quantity ax plus b is worth cx. Just a little hint, you'll have to combine things from a couple of the examples we've worked on. So go ahead and pause it, give it a spin, and we'll finish it together. Okay, welcome back. So this time, notice the variable they wanted isolated is on both sides. So I'm going to have to fix that before I do really anything else. So to get this over to the other side, though, I need to knock down these parentheses using our friend the distributive property again. So we have pi ax plus pi b is worth c times x. After that, I'd like to move all the terms with the variable x to one side. In this case, it would be easier to leave this one and only term that doesn't have an x where it is, move all of the x's, in this case, to the right-hand side. So I'll subtract pi ax on both sides. So then pi times b is worth cx minus pi times ax. And then we use our friend the distributive property again. So pi times b, pull the common factor of x, leaving us c minus pi a, and finish it off like we did the one above. Divide both sides by c minus pi a. Run out of room there, so we'll finish it over here. So x is worth pi b over c minus pi a. Be careful here. We cannot do any simplifying on this unless, of course, they give us some values for these things. You might notice that there's a pi top and bottom. Pi is indeed a factor of the top. Pi is not a factor of that denominator. If I had pi times c minus pi times a, then sure, I could factor a pi. But here it's part of a factor. Here it's part of a term, not a factor. Cannot simplify. So just kind of watch out for that. Okay. So we had a few that behaved as if they were linear. They weren't necessarily linear. The next one we'll do a little bit of a review with rationals. So we're going to solve for, in this case, theta. So do 1 over theta plus 5 over r is worth 6 over k. So here, excluded values, theta is non-zero, r is non-zero, k is non-zero. Otherwise, we're breaking the division by zero rule. Then, if you'll recall, we identified our LCD next. So in this case, that would be theta times r times k. So each term gets multiplied by the LCD. So we have 1 multiplied by theta rk over theta, plus 5 multiplied by theta rk divided by r, and 6 also gets multiplied by theta rk, and that one was over k. And we do r simplifying. Theta over theta is 1 since theta is non-zero. R over r is a 1 since r is non-zero. Similarly for k divided by k. So we have 1 rk plus 5 theta k is worth 6 theta r. So we have made it a little bit better. We took something that had a bunch of messy looking fractions in it. No more fractions at the moment. Then it's best, particularly in these multivariable problems, to take a peek back and remind yourself, okay, what is it they want? They are looking for theta. So I notice that this term doesn't have theta, these other two guys do, so I'm going to move the 5 theta k. So 1 rk, or simply rk, plus 5 theta k minus 5 theta k. It's worth 6 theta r minus 5 theta k. So r times k is worth 6 theta r minus 5 theta k. We're looking to get theta by itself, so we'll factor. So rk is theta being multiplied by both 6r and minus 5k. So our friend the distributive property, and then we're just dividing both sides by the difference of 6r and 5k. So then theta is rk divided by 6r minus 5k. Similar to the problem on the previous page, since r is not a factor of both terms down here, I can't cancel out an r. K is not a factor of both terms down here, I can't cancel out a k either. This is as far as we possibly go. So that was a little mini review on our friend the rational equation. Next up, we get to do a little mini review on our friend the radical or square root equation. So in this one, we're going to solve for a, and we're going to make an assumption. We're going to assume k is greater than or equal to 0. So square root of a squared minus b squared is worth k. So just like before, when we're solving square root problems, that first question is the square root alone. In this case, yes. So then, like the previous work we've done in this chapter, square both sides. So square and square root are inverse operations, so we're left with our argument a squared minus b squared. Right-hand side, k times k is k squared. We're looking to solve for a. This time I only have one term that has the variable we want by itself. So it looks like we're going to move that minus b squared. We undo subtracting b squared by adding b squared. And if I do it to one side, I must do that to the other side as well. So a squared is k squared plus b squared. We're getting closer, but we're not there yet. So then I want the a by itself. So we'll take the square root of both sides. Now later on, this is just a little preview. We'll see why I've included these guys. In 2.9, you're not going to be required to know why we're doing that yet. So a is plus or minus square root of k squared plus b squared. All right, so next up, we're going to solve a similar one, this time for q. And here we'll assume n is at least r. The square root of px plus q plus r outside is equal to n. So this time the radical didn't start off by itself. We have to fix that before we do anything else. So I'll subtract r on both sides. So square root of px plus q is worth n minus r. And then here's why we're assuming n is at least r. If n is greater than or equal to r, then the difference between those in this order would give us a positive or at least a 0. So it wouldn't give us square root equals a negative, which would kick us out of the real numbers. So after that, square both sides now that the radical is by itself. So px plus q is n minus r times n minus r. So px plus q is n squared minus nr minus nr again plus r squared. We just have a little bit of simplifying in the middle there that we can do. So n squared minus 2 of the nr's plus r squared. We're looking to solve this thing for q. I have only one term that has q. The px is in the way. I'm going to subtract px on both sides of the equation, and that will get us where we're going. So q, n squared minus 2 times n times r plus r squared minus p times x. And that's as far as we can take that one. All right, so next we look at a couple of formula applications. The first one dealing in temperature. So we're going to be given this conversion formula. F is worth 9/5 times C plus 32. So F is degrees Fahrenheit. And C is degrees Celsius. So we're going to find the temperature in degrees Fahrenheit for a temp of 30 degrees Celsius. So here, this is more just an application. We know one of the numbers, we're looking for the other. Fahrenheit, we don't know, that stays a variable. 9/5 is part of the formula. Celsius, we do have a number for that. That gets replaced with a set of parentheses, which we'll then drop in the number they gave us. And after that, we're just using order of operations to simplify since our variable is already by itself. So 30/5 is 6, so we have 9 times 6 plus 32. So F is 54 plus 32, so F equals 86. So the temp is 86 degrees Fahrenheit. So next we'll find the temp in degrees Celsius given a temp of 113 degrees Fahrenheit. So this time it's the 113 that we do know. The F we have a number for. 9/5 is just part of our formula. Celsius we don't know. That stays the variable then. And then we're just solving this thing for C. So I'll subtract 32 on both sides. So 81 is worth 9/5 times C. And then we'll multiply both sides by 5/9. So dividing by a fraction, remember, is the same as multiplying by its reciprocal. So 81/9 is 9, so we have 5 times 9 on the left side, 1 times C on the right side, so C is 45. So if you are in a different country that uses Celsius, spoiler alert, that's almost the rest of the planet. The US is one of the few countries that's still on Fahrenheit. If you turn on the news and they say it's going to be 45 degrees, going to be a warm one. Going to be pretty hot out that day. So the temp is 45 degrees Celsius. Now, if I wanted to do that with several different numbers, I could manipulate the formula like before. I could be asked to solve for C. So, remind you of the formula from the previous page. F is 9/5 of C plus 32. So, we'll just sort of mimic what we did on the other page. We'll subtract 32 on both sides. So F minus 32 is worth 9/5 times C. We'll multiply both sides by 5/9. And here we'll just do a little bit of distributing. Remember, if you want something to look like a fraction, you're always allowed to divide by 1. So 5 times F minus 160 all over 9 is worth C. One more short application problem. This is one that you should be comfortable with by now. Another common application, distance. Distance is rate times time. You've undoubtedly seen that in several other classes. In variable form, d equals r times t. So I'm going to ask you to do two things. I'm going to ask you to solve for t, and I'll ask you then to apply that and answer how long will it take to move 145 feet and 5 feet per second. Okay, so go ahead and pause it, see if you can answer those two questions. Welcome back. So our first one, d is equal to r times t, and we're solving for the variable t. Undo multiplication with division. So we just divide both sides by r. So t is d over r. Pretty short problem there. So with that in hand, now we can plug that in. Distance, 145 feet is a distance. Time, rate, 5 in feet per second. So the feet cancel. Dividing by 1 over a second is the same thing as multiplying by seconds. So 5 will go into 14 twice with 4 left over. 5 will go into 45 9 times with nothing left over. So it will take 29 seconds. Okay, that should be enough to have you work through section 2.9, the exercises at the end of the chapter. As always, if you have any questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.